Welcome to a lesson on vector projection. The goal of this video is to determine the projection of one vector onto another. So if we want to project vector u onto vector v, we use this notation here. Vector u is being projected onto vector v. Looking at the graph here on the left, we're projecting the red vector u onto the blue vector v, and the projection is the gray vector, which we call vector w sub 1. So to emphasize this, the projection of the red vector onto the blue vector is this gray vector here. One way to think of a projection of one vector onto another is if we were to have a light up here and it was shining down on the red vector, the projection of u onto v would be the shadow that this light produces. We can also think of the projection as the vector component of u along v. Looking at the second diagram, if we had a light up here and projected vector u onto vector v, this light would produce a shadow in the opposite direction of vector v. Again, the projection would be this gray vector here, vector w sub 1. So the projection doesn't necessarily have to be in the same direction, but it would be a scalar multiple of vector v. The next thing we want to mention is that vector w sub 2 is called the vector component of u orthogonal to v. And we can find w2 by taking vector u and subtracting vector w sub 1. So again, the highlighted gray vector would be the vector component of u along v, and the vector component of u orthogonal to v would be vector w sub 2, would look something like this. Again, notice that the green vector is orthogonal to the blue vector, and vector w1 plus vector w2 does equal vector u. On the second sketch here, vector w sub 2, or the vector component of u that's orthogonal to vector v, would be this vector here. Again, notice it's orthogonal or perpendicular to vector v, and vector w1 plus vector w2 would equal vector u. Now let's go ahead and take a look at a formula that will allow us to find the projection of u onto v. If u and v are non-zero vectors, then the projection of u onto v is given by this formula here. Notice that the projection of u onto v is going to be a scalar multiple of vector v. The dot product would be a numerical value, and so would the magnitude of vector v squared. Let's go ahead and use this formula to find some vector projections, and then we'll take a look at it graphically as well. First, we'll take a look at an example in R2. We want to determine the projection of u onto v given these two vectors, and then determine the vector component of u that's orthogonal to v. So here's our formula to determine the projection of u onto v. It's going to be equal to u dotted with v divided by the magnitude of vector v squared times vector v. Let's go and determine the dot product. So u dotted with v is going to be 3 times 4, that's 12, plus 1 times 2, that's 2, divided by the magnitude of vector v squared. Remember, the magnitude of vector v would be the square root of 4 squared plus 2 squared, but if we're squaring the square root, we're just going to have 4 squared plus 2 squared. And then we're going to multiply this scalar by vector v, which is the vector 4, 2. Let's go ahead and determine what this scalar would be. We're going to have 14 divided by 16 plus 4, that's 20. This fraction simplifies, that'll be 7/10. So if we multiply this, we're going to have 28/10, that will be 14/5, comma, 7/10 times 2 would be 14/10, or 7/5. And we'll go ahead and let the projection of u onto v be vector w sub 1. Now we want to determine the vector component of u that's orthogonal to v. We'll go ahead and call that w2. And that's going to be equal to u minus w sub 1. So we're going to have vector 3, 1 minus the vector 14/5, comma 7/5. So vector W2 is going to equal 3 minus 14/5, that'll be 1/5. And the y component will be 1 minus 7/5, or negative 2/5. So again, here's the projection of u onto v, and then here's the vector component of u that's orthogonal to v. Let's go and take a look at the graph of this. We're projecting the red vector onto the blue vector. The projection of u onto v would be here. The orthogonal component, or vector w sub 2, would be here. And we can see that w sub 1 plus w sub 2 is going to equal vector u. So here's a nice illustration of what we just found. The projection highlighted in yellow and the orthogonal component in green. Let's go ahead and try one in R3. We want to find the projection of vector u onto vector v. So go ahead and call the projection vector w sub 1. So the numerator will be u dotted with v, so we'll have 1 times 5, that's 5, plus 2 times 4, that's 8, plus 1 times 2, that's 2. Divided by the magnitude of vector v squared, that'll just give us 5 squared plus 4 squared plus 2 squared. We're going to multiply this by vector v, which has components 5, 4, and 2. Let's go ahead and simplify this. We're going to have 5 plus 8 plus 2, that's 15, divided by 25 plus 16, that's 41, plus 4, that's 45. This simplifies to 1/3. So this is going to give us 5/3, 4/3, and 2/3. Again, this is the projection of u onto v, which we're calling w sub 1. So now to determine the vector component of u orthogonal to v, we'll call it w sub 2. It's going to be equal to u minus w sub 1. So we're going to have 1, 2, 1 minus 5/3, 4/3, and 2/3. So we'll have 1 minus 5/3, that's going to be negative 2/3. We'll have 2 minus 4/3, that'll be 2/3. And 1 minus 2/3 is 1/3. So again, here's our projection of u onto v. And here's our vector component of u that is orthogonal to v. Let's look at this one graphically as well. It's a little bit harder to interpret in 3D, but if you project the red vector onto the blue vector, the projection would be this gray vector here, which we called vector w sub 1, and then the vector component of u that's orthogonal to v would be this green vector here, which we called vector w sub 2. Okay, that's going to do it for this video. I hope you found these examples helpful. Thank you for watching.